Hello students, welcome back to our lecture on Gaussian plume in the course Environmental Modeling and Simulation. In the previous class we talked about conservation of mass and how we applied them in different kinds of reactors, and in this class we are going to continue our discussion on a contaminant that is released by a chimney or a stack in the fluid, and the fluid we are talking about is air. And I have titled this class as Gaussian plumes in the air, because we will notice that given our assumptions we will end up with the plume that is Gaussian in nature. Okay, so let us get started. We have a chimney and the chimney is releasing smoke, and we want to find out the concentration. So, we know the emission rate, we want to find the concentration of a contaminant that is being released for given XYZ. Basically, for given point in the space we want to know the concentration of the pollutant that is emitted by chimney. We are going to make tons of assumptions, but first let us try to understand some other factors that will affect the way in which the pollutant spreads in the atmosphere. We have talked about meteorological conditions. We also need to, and we have also talked about some other factors like the height of the chimney, the temperature of the smoke coming out. We also need to look at other kinds of factors. Sometimes some contaminants will degrade very quickly when they come in the environment. They might even make secondary contaminants. So, if the contaminant itself is undergoing change, we need to look into that. Then the other thing we want to look at is the size and the weight of the contaminant. If the contaminant is big enough or heavy enough to settle down closer to the earth, then the plume will naturally gravitate towards the earth's surface. Okay. The next thing we need to look at is how the air will spread. Now, the plume or the spread of the contaminant once it is released from the chimney will depend upon two things. One is the transportation by wind. If there is wind in the environment, which there typically is some kind of bulk action going on, then that wind will carry the smoke in the direction, downwind direction. So, now in this particular diagram, cartoon sketch that I have made, it is assumed that the wind is moving in this direction, the direction shown by the arrow, and the wind is transporting the smoke, and as the wind is transporting the smoke, because the smoke is having higher concentration of certain compounds, certain contaminants, they are spreading in all directions, laterally, vertically, and also is basically in XYZ direction. Now, so already we know that there are two major kind of factors that determine, that show the spread or the transportation of the contaminated environment. One is the bulk action, the other is diffusion. So, bulk action is when a carrier like wind, or in case of a carrier like wind, or in case of a river we have water, is carrying the contaminant from one end to the other. So, that will determine the shape of the plume, the shape of the smoke as it travels downwind. The other is diffusion. Now, bulk action happens because the fluid in which the contaminant exists, that fluid is moving. So, in case of groundwater, the groundwater is moving. In case of river, the river water is moving. In case of air, the wind is blowing. Now, diffusion happens because of random molecular motion. So, if you remember your basic science, Brownian motion, things undergo Brownian motion, it is a random motion, and it is so that because of this random motion, the contaminants or the compounds we are tracking tend to move from higher concentration to lower concentration. In fact, one of my favorite phrases in this field come from diffusion concept, which is nature abhors gradient. I do not think nature has emotions like abhorring, and I do not think nature has emotions and it will abhor gradient, but it does tell me that diffusion, the net movement because of diffusion will always happen from higher concentration to lower concentration. Now, in this case, even though wind is traveling, wind is taking the smoke from chimney to downwind direction, in all XYZ direction, the wind, regardless of the wind motion, there will diffusion will happen, and it will take the smoke and the contaminants away from the plume towards lower concentration area. In diffusion, we use a very simple law given by Adolf Fick, and it is called, I think it was in year 1355, and it is called Fick's law. And we are going to use that law to start deriving our Gaussian plume model. But before we do, we need to look at some other part of the bulk action. So one bulk action is happening because of the wind in this case. There is another bulk action happening which is known as the stage 1 of transportation of plume, which is plume rise. Now when the smoke comes out of the chimney, it undergoes a certain level of rise, and that vertical rise is known as plume rise, and there are two reasons why it will go through plume rise. First is it has momentum. Remember Newton's law of motion. Things in motion want to stay in motion. The momentum is conserved. So the smoke is coming out with a velocity. There is a velocity of this at which the smoke is coming out, and it wants to continue in the upward direction. So that is one of the reasons why it will move up. So plume rise, let us say del H. Del H is the increase in height of the plume beyond the height of the chimney. Let us say the height of the chimney is given by capital H, and the plume rise is given by del H. So the plume will rise beyond the chimney and it will reach till del H for two reasons. One is momentum, del H due to momentum. Things in motion want to stay in motion unless external force is applied. The external force here would be gravity, the external force here would be the friction, the drag. So one is that reason. The other reason is many a times the smoke is warmer than the air around it. So we have thermal buoyancy. So thermal buoyancy is hot things tend to move up, cool things tend to stay down. Hot things, they tend to expand, hot gases tend to expand, they tend to move up, cool air comes down. Since the smoke is warmer, it will rise up, and it will rise up until its temperature is same as the temperature of the air around it. Of course, as the smoke rises, it starts losing its temperature, which follows a lapse rate called adiabatic lapse rate. Now depending upon the kind of smoke, whether it has moisture in it or not, it might undergo cooling according to dry adiabatic lapse rate or according to wet adiabatic lapse rate. The momentum depends completely on gravity and on the drag that the smoke will face as it is emitted out of the chimney. We have three formula here for you, empirical formula for plume rise. Now each of them are empirical, so of course that is why we have three. If it was not empirical, we would have one. And what I want to do is take some time to look at each of the empirical formula and notice which part of the formula is talking more about the physical momentum mv, and which part of the formula is indicating about thermal buoyancy. The first formula is Holland's formula. Okay. Holland's formula looks like this: del H, which is del H due to momentum and also del H due to thermal buoyancy, is equal to Vsd by U. Vs is the velocity of smoke in vertical direction, U is the wind velocity in horizontal direction, d is the diameter of the stack at the top, d is the diameter here, U is the wind velocity, and the V is the velocity at which the smoke is coming up. Okay. So this is Holland's formula, and we are going to take a closer look at this formula and try to understand which part of the formula is talking about the plume rise due to momentum and which part of this formula is talking about plume rise due to thermal buoyancy. Now notice, since they are empirical formula, this is what we know works by our experience. We do not have very conceptual backing of why it is 2.68 into 10 to the power minus 3 and not 2.65, but this formula works pretty well. It is also one of the most commonly used formula for plume rise. Okay. When we take a closer look at it, clearly this is talking about Ts, the temperature of smoke, minus temperature of air divided by temperature of smoke. So it is talking about how much warmer is the smoke compared to the air around it. This part is talking about thermal buoyancy. So this factor is definitely talking about thermal buoyancy. The warmer the smoke is compared to the air around it, it will rise. I mentioned, let us say the air itself is 40 degrees or 45 degrees. At the time of recording, the part of the country that I am recording in, North India, the temperatures have reached 45 and above multiple times during the summer. So, let us say the temperature in the atmosphere is 45 degrees, the smoke is at 40 degrees. 40 degrees is quite hot smoke, but it is cooler than the air. So, it is not going to rise due to thermal buoyancy. In fact, this particular term will become negative in that scenario, even though the smoke is hot. Now, the same chimney in winter will have a very different effect. So, let us say in winter the temperature of air is 15 degrees and the smoke is again coming out at 40 degrees. Now, the smoke is much warmer than the air, so it is going to rise up. So, same smoke, same chimney, same industry, same temperature. If the ambient temperature changes, the plume rise will change, because the plume rise accounts for thermal buoyancy, which is relative. So, it talks about the smoke versus air, which is warmer. Now, this part of the system, which is 1.5 VSDU, talks about velocity of movement, bulk action in two directions. One is Vs, which is moving up, one is U, which is horizontal movement. What we are noticing is here that there is a movement, there is a reason, there is a bulk action going vertically, which is Vs is in numerator, and then denominator we have the horizontal bulk action, which is due to the wind. As the plume rises, the wind is taking it downwind. Now, if the velocity at which the smoke is being released is very high, we will see that the net plume rise will happen in vertical direction before it starts moving downwind, or as it starts slowly moving downwind. However, if the wind is very high and the relative to the velocity of the smoke, then we will see the net motion will look like will be more flatter, the plume rise will not be very pronounced. Now, one way to look at it is incense sticks. So, if you have access to an incense stick and you can safely burn it, please be safe, not asking you to play with fire, and you burn the incense stick in a room or in an area with no wind. So, no fan, no one is blowing at the incense stick, let us say in an enclosed area, you will see that the smoke will rise, and it will rise before it moves in either direction, laterally, horizontally, and it rises because the smoke is warmer than the air around it. Now, since the wind is zero, we see a pretty good vertical rise, pretty good plume rise of the smoke. Now, if we slowly blow at the incense stick very gently, we don't want to be very rough here. If we slowly blow at the burning incense stick, we will see that the plume will suddenly turn flat. So, now the smoke that was supposed to rise is moving mostly first in the horizontal direction. What we have done is we have increased U dramatically. So, instead of a rise that looks like this, the plume looks like this. So, there is negligible rise. This is a very important part of Holland's formula, Vs by U, and Vs by U is multiplied to both thermal buoyancy and to this factor 1.5, which means regardless of the thermal buoyancy, the smoke may be very hot, but if the wind is very high, it will flatten out the plume rise. If the wind is barely there, it will rise even if the smoke is not much hotter than the air around it. Okay, this is the first formula, the Holland's formula. Now, let us take a look at the second formula. The second formula is Carson and Moses formula. Students, I do want to mention here that if I ask you to calculate plume rise in the exam or in the quiz, I will give you the formula. So, you do not need to cram them, but it is important to take a look at them and understand what they are saying. Even if it is an empirical formula, it can inform us a lot about what factors are important, and our background in modeling that we have already gathered through this course should be enough to give us an idea of how to model the phenomena. So, this is a situation where empirical formula can help us develop better fundamental understanding, which we can use to model better models and improve our empirical models, improve our empirical formula. Okay, Carson and Moses formula, del H is equal to minus 0.029. Look, there is a minus sign here, VSD by U plus 2.62 QH 1 by 2 by U. Okay, I need to introduce you to this new term QH. QH is thermal flow rate. It is the rate at which heat is flowing. Again, it is indicative of thermal buoyancy. Right here, I know that this term is talking about thermal buoyancy, and this term is talking about momentum. Now, one thing that we need to look at, thermal buoyancy, because we are using QH, it is not just about temperature, it is also including momentum. It is both physical momentum and thermal buoyancy. In Carson and Moses, they have one term that QH, one factor that includes both thermal buoyancy and the flow rate. And then we have an additional term which is VSTU, and it has a very small coefficient attached to it compared to this, and it is negative. So, there is some damping effect happening. So, in this case we know that this is a momentum term, but the more important momentum term is this one, 2.62 QH to the power 1 by 2 divided by U, which is the horizontal velocity of the wind. The third formula that I am going to give you is concave formula. I do not know how to pronounce the name of this scientist, and it is much simpler than all other models, all other formulae, but again you do not need to cram it. Now, this looks very similar to what we saw here in the Carson and Moses formula. We have only one term, we do not have two terms, and this term accounts for both thermal buoyancy and momentum, because QH is the heat flow rate, which of course incorporates the mass of the smoke. The more mass, high temperature, QH will be higher. Less mass, same temperature, QH will be lower. So, now it is also, notice also that the power of QH is also quite comparable, and U is less important than it was here. So, we do not have this damping term. So, concave model is sort of an improvement over Carson and Moses formula. However, the most commonly used formula is Holland's formula. Regardless, if I do ask you to calculate Plume rise, I will give you the formula and I will ask you which one to use. Alrighty. So, we have gotten through the Plume rise. Now, let us look at the second stage of the motion, the transportation of the smoke once it is emitted from the chimney. So, just as a reminder, stage 1 was Plume rise. And then stage 2 is the spread, dispersion. And as I mentioned earlier, there are two reasons why the smoke will spread, or the technical term is dispersion. The first is diffusion, which is because of random molecular motion, the Brownian motion, and the net effect of the random molecular motion, random Brownian motion, is movement of molecules from higher concentration to lower concentration. So, against the concentration gradient, and we are going to use Fick's law for this. And then dispersion, we have bulk action. Now, in case of air pollutant, bulk action will happen because of wind. Now, in case of chimney, the wind is taking the bulk action of the wind will take the pollutant, the smoke, downwind. If you add the diffusion and bulk action, what you get is dispersion. Okay, so now let us start. So, let us say we have a chimney here and it is emitting. So, first it undergoes some kind of plume rise. So, the height of the chimney is capital H, the plume rise is del H, and you calculate it using either of the three formulae. We will see which formula is more relevant, and that is why we do experiments. And then it starts going through dispersion, and the dispersion is happening due to diffusion and bulk action. Clearly, by looking at the diagram, you can tell the wind is blowing in this direction. So, let us define our coordinate axes. Let us say the direction of the wind is x axis, perpendicular to it horizontally is y axis, and going up vertically is z axis. So, this is our coordinate axis. Now, let us take a small parallelopiped of air here. Okay. So, let us zoom into this parallelopiped. Okay. Let us say the volume of this parallelopiped, we can calculate it. So, let us say in x direction the length is del x, in y direction the length is del y, in z it is del z. So, the volume of this parallelopiped is given by del x into del y into del z. It is a very small parcel of air, and the entire atmosphere can be modeled as series of similar parcels stacked next to each other. And what is happening is movement of smoke or contaminant from one end of the parcel, one end of the parallelopiped, and out to the other end of parallelopiped into the stack that is next to it. So that is what we are going to do. We are going to take this del x, del y, del z verified as a control volume, and then we are going to integrate it for the entire atmosphere. Now we are going to use Fick's law. Remember, Fick's law says that the movement will happen against the concentration gradient. So let us say the concentration gradient is given by del C del x. So clearly the movement will be the flux, the flow of the smoke or the contaminant that you are tracking will be in the direction opposite to the concentration gradient. Remember, nature abhors gradient, things are moving from high concentration to low. Concentration gradient is from low, is positive from low concentration to high. The flow is opposite to that. The constant that we use here for the flux, so let us say we are starting with x direction first. Remember, x direction is here, this is y, and this is z. So in x direction, flux Fx coming in is proportional to minus del C del x, and then we have a diffusion constant minus sign. Dx is a constant that we are using in this Fick's law, and this is known as the diffusion constant. Remember, we are first writing down the diffusion part of the dispersion, and then we will write the bulk action part later. But right now we are focusing on the diffusion part. We will add the bulk action, so do not worry. So there are with dispersion through this end, there are two things happening. One is through diffusion, DIFFUSION, the other is due to bulk action. So diffusion part is this, the bulk action part would be the concentration of the gas here, C, wind velocity. Now this is per unit area, flux is always per unit area. So what we want to do now is multiply it with the area of this face. What is the area of this face? Del y into del z. So this is no longer just Fx. So minus dx del C del x plus Cu into del y del z will tell me the flow rate in through the this face, this one face of the parallel pipe. We are going to do it with all faces in all directions x, y, z. Right now we are writing for x, and then similarly we will write for the others too. Okay, now this is incoming mass coming in. Now there is a mass going out also in x direction. So let us say the net mass coming in here is nx, and due to diffusion, and then due to diffusion here will be nx plus dx. Now we need to find out nx plus del x. Now this is where it gets slightly tricky. To find nx plus del x, we are going to use Taylor's theorem. So let us look at how that works. So the Taylor's theorem tells us that if we know Fx, then Fx plus del x can be easily estimated using Taylor's expansion of Fx plus del x, which is Fx plus del x f dash x, and then some higher order terms. Since del x is very small, as we go into higher order terms, they will be most likely negligible. We are going to neglect them, and we are left with this. So we want to find out mass in minus mass out with respect to time, first in x axis and then y axis and z axis, and we are only focusing on diffusion right now, even though in the previous slide I talked about bulk action also. So mass in minus mass out in this case would be mass coming in was, remember, nx, mass out would be nx plus del x. So we know that using Taylor's expansion we can write nx plus del x is actually equal to nx plus del x n dash x plus some higher order terms, which we are going to ignore. We can ignore this as long as this is not 0. Del x is not 0, as long as the derivative of nx is also not 0, we can ignore the higher order terms. Now we want to find nx minus nx plus del x, so we can use this equation. We get nx minus nx plus del x by bringing this here and by taking this here is equal to minus del x first derivative of x nx. So we are going to use this to in our Fick's law to understand the flow, the net flow of mass in x direction due to diffusion. So remember, the flux due to diffusion was given by minus dx del C by del x. Now, here we are assuming that dx is constant in the x direction, which may be true for certain fluids, but is not always true for air. So, it would be more sensible to write it like so, like so. Now, if we, because flux is per unit area, we multiplied area. So, we made it Fx del y del z, which is the area of the face of the parallelopiped that is perpendicular to the x direction, is equal to into del y del z. Okay. Now, we are going to use this to get the net flow in x direction due to diffusion. So, that is going to be, this is Nx. We have a minus here from here, del x into derivative of del y del z, which will come out of the derivative. So, we have minus del x del y del z, derivative of this. Okay. Now, we are going to make another assumption here. We are going to assume, which is not always true in case of atmosphere, but it is true for distances less than 100 meters and distances more than 10 kilometers typically. Not always, but under typical environmental situation where we have moderate lapse rate, moderate atmospheric condition, dx will be constant in x direction for up to 100 meters and then beyond 10 kilometers. So, under that assumption, so please write down this assumption in your notes, that we are assuming dx is constant. So, what this will transform into is dx will come out of the derivative and we will have double derivative of c with respect to x. This is in x direction, this is due to diffusion, not the bulk action. Bulk action I will add later. Now, let us write similar for mass input dm by dt, which is given by nx minus nx plus del x in x direction. Let us write it for y and z direction. So, nx, to summarize, okay, one thing that I forgot was a minus sign here, so they will get cancelled. So, we have we can write similarly for y direction, mass in minus mass out, remember, and we are only doing for diffusion right now. In the next lecture, we will do for bulk action. Again the same assumption, dispersion coefficient, the diffusion coefficient in y direction is constant. And then same in the z direction, same assumption for the z direction. Now, the net movement of mass due to diffusion through the parallelepiped will be summation of all this. So, dm by dt due to diffusion will be summation of all this. So, let us add all of these. So, diffusion related n through the parallelepiped del x del y del z is given by, let us take del x del y del z common because it is common in all, and then we have dx del square c by del x square, dy del square c by del y square, dz del square c by del z square. This is not square, this is double derivative. Okay. We will end here in this lecture. In the next lecture, we will also incorporate mass action, put them together, integrate and get our Gaussian Plume model. See you in the next lecture. Thank you.